Great, well, thank you very much. So today I'm going to speak about concrete performance and action. So thank you very much, Chris, for the kind introduction. And I'll speak a bit about our work, particularly in relation to tailored reinforced concrete infrastructure today. So the CO2 impact of cement is very large. It's responsible for 5 to 7% of our global CO2 emissions. And that's also reflected through the very large volumes of concrete that we use globally. One of the things about concrete, which is both a strength and a challenge, is that it covers a great many materials. So there's infinite number of possibilities. No two concretes are alike. We can have different cementitious binders, different mixed proportions, different aggregates, and different ways of processing. So the opportunity amongst this is that we can actually look at the performance of concrete in a very detailed way and make choices accordingly. And so these themes of performance and eco-efficiency are very much germane to this presentation that I'll give today. One of the interests at the moment is tailored reinforced concrete infrastructure. What we're looking through our tailored systems is to reduce the embodied CO2 of concrete products. And we do this by using multiple mixes within a single element, primarily looking at wet casting. So this is functionally graded concrete, where we accept the idea of having more than one concrete mix within a single element. And why that's so powerful is we can now use that flexibility about concrete to design concrete materials to meet specific performance objectives, which may vary amongst an element or a structure itself. And really the overarching idea is to only use higher cement contents where absolutely necessary. To give you an idea of the sort of elements we're thinking of, that this is an environmental shielding prototype. In this case, we have an outer protective layer of concrete with a high cement content to give us a durability performance. And then we have a lightweight core with lower cement content for the bulk material. And I'm going to come back to this example a little later. So when we're looking at these elements, we come back to these two key questions. What performance is required and how can this be met with the lower embodied CO2? So for the remainder of the talk, I'd like to pick up on those questions in the context of three strands: quality control and uncertainty reduction, multiple performance requirements, and new innovations. So let me start with the first one about quality control and uncertainty reduction. If we look at these ideas, and this is work that one of my students, Ma, has kindly prepared for me. If we take an example, and we can take other examples, but looking at a CEM1 C3040 mix, and let's think about the idea of quality control. So what this plot is on the vertical axis, we have probability density, and on the horizontal compressive strength. So these probabilistic distributions, normal distributions, would show us that within either excellent, which is the blue, good, which is kind of the orangey color, or poor, which might be that we have a bit of shovels full of cement and aggregates and sand and a bit of water, we see that we get very different distributions. So if we were to test multiple concrete specimens with each of those types of quality control, we'd see this sort of scatter. But what that means is that actually with higher quality control, we can have a lower cement content because we don't have such variability. And for this particular example, we could get away with 310 kilograms per meter cube with excellent quality control, whereas with very poor quality control, we would have 346 kilograms per cubic meter. So there's a cement penalty by having poor quality control. Now, this is known and reflected in our guidance. So for example, in terms of the ways to specify concrete, if we look at standardized prescribed concretes or ST concretes, they accept that these might be small batches, hand mixing, whereas our designated concretes with predetermined ideas, the equivalent of a ready mix in a gen class are provided. So these differences are known. And indeed, if we look at the Concrete Centre Specifying Sustainable Concrete document, we, if I may read it, it says to ensure the ST designation recommendation is safe for the indeterminate range of materials and site supervision, the prescribed cement content is very high. And the use of ST concrete should be avoided when a ready mix concrete in the form of a designated or designed concrete can be used. Standardized prescribed concretes, so that's the ST class, have a much higher embodied carbon than the equivalent designated concrete. So we see that this is implicit in this guidance. And I think what I've picked out and the different values for the different classes, but for example, for ST4, which might be trench fill, for example, we have a minimum cement content or combination of 330 kilograms, whereas for Gen 3 equivalent, we have 220 kilograms. So if we look at this difference, it's significant. So if we move from an ST to a Gen 3, there's a 30% reduction in the cement. And indeed, we want to go even further. We don't want to stop at Gen 3. Many ideas of sharpening our pencil and looking at supplementary materials will take us to much lower values than that. And that indeed is on all our targets and projections for what we need to do in the future. But I think if I can pause at this point to say we should be doing these big steps now, and this comes up to a point that's come up in conversation already, is that making changes today can have an impact. And indeed, one of the things we have found is there's some information to suggest that we're getting ST concrete supplied ready mix in the UK, which would mean that we're getting a cement penalty for that when it would be unnecessary. And so we're trying to probe that question in more detail. So if anyone on this call has some insights about that, we'd be very pleased to hear from you. So if the next strand I'd like to pick up is the multiple performance requirements. And if we think about these performance requirements in terms of the material, we might have, and I've just picked a few here, ECO2, strength, durability in terms of carbonation resistance, durability, chloride resistance, workability, slump, etc. And where we get complexity is looking at this multi-criteria question. So we've got a criteria question about the structural form, and we also have multi-criteria question about the materials. And I'd like to pick up a little bit of how we've started to look at these multiple dimensions in the context of these three particular performance requirements, the ECO2, strength, and carbonation resistance. So this is work from Jessica Forstack, again, another of my PhD students. And what she's done is she's looked at a number of papers in the literature, and she's extracted the constituent materials from those studies, and also their measured cube strengths. She's then calculated what the embodied carbon is. In this case, it's kilograms ECO2 per kilogram concrete, and that's the vertical axis, versus the concrete strength. And you see we get a scatter of materials. So if we have a particular strength requirement, again, I've just picked something, so say 50 MPa, you see that there's choices available within this, which have a higher embodied carbon or a lower embodied carbon. But the question is much more complex, because we've already been hearing about how if we have a column, it might be actually the best decision is to overall reduction in embodied carbon is to use actually a high cement content, but a much smaller volume of concrete. So these again are aligned to what we need to do structurally as well, as to which of these mixes is the best in terms of the overall system and reducing the overall CO2. If we now put in, say, for example, a durability requirement, in this case, a carbonation resistance. Carbonation is typically modeled using a 1D Fickian diffusion model, where we look at carbonation distance, which is XC, proportional square root of time T, through a constant carbonation coefficient K. And there's a little icon on the right of this slide to show you what that means. So I think for the purposes of what I want to describe next, the key thing to think about is, say, if we have a particular design life, so that fixes T. If we then have a carbonation front requirement, then we can actually work back to find out what K would be. And in the sense of a progression of a carbonation front, again, if we fixed time, a lower K would mean a lower XC, hence a smaller carbonation front. A higher K means a higher XC, hence a carbonation front that has progressed further into the structure. So generally, a lower K is better carbonation resistance, higher K is poorer carbonation resistance. So Jessica's then taken the data we just looked at and tried to then add this third dimension to it. So what I'm now plotting here is we have these quadrants of low carbonation resistance, low strength, high carbonation resistance, high strength at the other diagonal. So what we've got, carbonation coefficient K versus a strength 28-day. But what's been added here is this color coding. And so this is now the CO2, the kilograms ECO2 per kilogram concrete. And in fact, the yellow colors are the higher values and the blue colors are the lower values. So again, we could work back to find what carbonation coefficient we need. For the purpose of this, I've picked one, which is then a horizontal line of some description. And then we can also put on our strength. So now we have a strength and a carbonation resistance. And then within that space, we'd be looking for the lower carbon options, which would be the more blue colors. So once we start looking at multi-criteria performance, we have to do it in a very intelligent way, because we are trading off different material resistances, and also the overall structural form itself, amongst many other criteria. So then the final piece I'd like to pick up in terms of performance is how can we think about performance-related design also embracing new innovations? And so I'm going to use my tailored infrastructure example to talk that through. So if we come back where we have a protective outer layer of concrete with high cement content, a lightweight core with lower cement content. And really what I challenge you is a thought experiment. So we've got a higher ECO2 in this kind of pinky reddy colored mix, and then we've got a lower CO2 in the gray mix. So let's say we selected those two mix and they have the same 28-day cube strength. Are we comfortable with the fact that on a performance equivalent strength basis, that would be the same performance, say, as a material, all a cube with a single material, say mix 1. Okay, and next thought experiment, again, ECO2 mix 1 higher than ECO2 mix 2. What if we now bring in a carbonation resistance? So let's say the carbonation resistance, i.e. lower K, is better for the pinky mix than the gray mix. Are we then comfortable with the idea that the carbonation resistance of the tailored element is equivalent, say, to the carbonation resistance solely of mix 1? And you might say, okay, if the carbonation fund hasn't progressed into gray material, I'm happy with that. But if it does progress into the gray material, I'm not happy with that. So what do we now mean for equivalency of performance when we start to think of new innovations, both in terms of the materials, the structural forms, and how we put together our structural elements? And so it comes back to, are we happy with this? Maybe or maybe not. And we might have additional considerations we'd investigate, the integrity of the interface, the composite action, no detrimental failure modes, et cetera, et cetera. But I think the key thing in this is that unless we present performance-based design in the sense that we can bring in kind of novel innovation, we have a risk of locking in what we're doing now simply because we're not thinking widely enough about performance. So in summary, come back to these two key questions. What performance is required? How can this be met with a low and embodied CO2? I think we've got this strong point coming through. Let's use best practice today, sharpen a pencil, state of the art, make those savings now. We've got frameworks for multi-criteria performance that we have to put in, and we need to think about performance-related design for emerging material and structure innovations. So I'd like to say thank you to a great many people, and thank you very much for your attention.